Brilliant. Well, thanks for all coming. It's great to hear now. I'm Sean, CTO at OSO. We run the meetups in London, or we do them monthly actually. So this is a bit of a tour for me coming to Oslo. Thank you, Dino, for hosting us today. Yeah, brilliant. Thanks very much. Rapid time. The first talk tonight is by Axel and Helman. So I'll hand over to these guys. Okay. Cheers.
Right. Should I take the mic or?
Yeah.
Yes. Okay. Hello, everyone. We are going to talk about Statnett's project for automating power balancing. And that's basically how we ensure that Norway has available electricity without the country going dark. So in particular, we'll focus on how we use the TopologyTestDriver class to ensure that our Kafka streams are robust and reliable enough to support the future of power grid regulation. And by we, I mean the teams that me and Herman are working in. This might not be the best solution for everyone, but it's what we do and it works well for us. And yeah, my name is Axel. I have a master's in energy and environmental engineering from NTNU. I've been working as a software engineer the last 3 years for Statnett, in particularly what's now called Team Balance. And for the context of this talk, I'd like to mention that I hold the Confluent certification for Apache Kafka developers. I also like to play chess. This is me from 2 years ago at JavaZone. So if any of you are attending the conference this week, I'll be more than interested to play.
Yeah, my name is Herman. I have a degree in cybernetics and robotics, and I currently work as a tech lead for one of the teams at Statnett. I too also have a CCDAK, and it's almost 2 years old, so it's time for me. And yeah, in my free time, I like to watch and play football. Just pretty basic stuff.
All right. So before we go into the more technical things, I'd like to talk a bit about what Statnett does. Statnett is responsible for building, maintaining, and operating the power grid in such a way that the power consumption is always balanced out by the power production. And we've been doing this for a long time by having operators manually ordering power plants to decrease or decrease their production as the demand changes. But we're now facing a big change in how these balancing operations are being conducted. And there's multiple of reasons for that. Some of them are the advent of non-dispatchable power sources like wind and solar, not only in Norway, but also the countries we are connected to. And these power sources makes it a bit like they fluctuate, so it makes it more demanding to balance the power grid. And another big change is that we are moving towards what's called flow-based coupling, which means that instead of have a more or less fixed power in capacity, we will now calculate the capacity based on how much electricity that flows in the grid. And this allows us to use the grid more effectively, but it also increases the risk of overloading. And this risk needs to be managed properly. And another big change is that the options that the operators has available to regulate the grid is going from being changed every hour to be changed every 15 minutes, which means in practice that the operators will have a quarter of the time they do today to keep up with the changing options. So yeah, some of all of this, the status quo will no longer be sustainable and automation is required.
And yeah, so the automated solution is data-driven with real-time data. So this figure is trying to illustrate a very simplified overview of how the automated solution works. Here on the left side, we have the power grid with a lot of sensors, which continuously measures how much power flows through all the lines. And this real-time data goes through the SCADA system of the Statnett and to my and Axel's team. So we enrich the data, aggregate the data, filter the data, ensure that the data has adequate or good quality before we send the data to the operators which can see how much data goes through the power lines. And the data also goes to machine learning models, which are trying to predict the imbalance in the power grid system. And the thought is that the machine learning models will be able to have some automated actions which will balance out the imbalances. So the tech stack in Statnett, we have an on-prem self-managed Kafka cluster. And our team mainly develops Kafka Streams applications as microservices. So as said, we enrich data from other sources and aggregate data. And we also use consumers and producers when we wish to get data from external systems. But the key point here is that, as you can see, we're kind of like the central nerve in this whole control system, feedback loop, whatever you want to call it. So we need to ensure that our applications are working as intended. And how do we do that, Axel?
Well, that's exactly what we're going to show you today. So we have prepared a demo application, which is basically a simplified example of the types of applications that we make. The case we have is that we need to filter. We are subscribed to a data stream of power grid measurements, and we want to filter away the bad quality measurements and passing that along the stream. And this data is Avro encoded. And we're going to show you some different types of topologies to accomplish this task. And most importantly, we will test them with the TopologyTestDriver, which is a native class from Apache Kafka. So with that, I think we are ready to show you a bit of how the application looks, and then I will attempt to live code one of the tests for you.
So fingers crossed.
Yes, yes. 90% success rate, all we need, right? All right, so we can start with showing you the Avro scheme that our measurements are made in.
Yeah, so this is like the data or simulated data that we get from the power grid. We have 4 fields. So the first one is an MRID field, which is like the identifier for the sensor, so we know which sensor is providing the measurement. We also have a value, which is the power flowing through that sensor. And we have a flag saying whether the sensor is working or not, if we can trust the measurement. And lastly, we have a sample timestamp saying when the measurement was taken.
Okay, so then we move on to how the topology looks.
Yeah, so this is our very complex topology, Kafka Streams. It consists of 3 steps. First, we consume a topic. This is where our data are input. And then we do a filter where we only take the measurements that are valid. And lastly, we produce it out to another topic, which can be consumed by, for instance, the machine learning team.
Yes. So now that we have our topology, we want to test it to ensure it works correctly. So here I have this class that we will fill out, and I've written a little list of the different things we need to configure before we can start the unit test itself. So I'll just jump into it and do some coding. So the first thing we need is that we want a way to produce the data that we're sending through the topology. So we use our own class that we call record factory. And what this basically does is a simple class that contains a function that returns an object of the Avro type that Herman talked about. So next, we need to set up a schema registry for this unit test. And that is a bit, it has some steps to it. So we have the schema registry, and we define a scope, which I'm going to cheat a little bit to make because that's a tricky thing. And with the scope, we're going to make the schema registry URL, which basically takes in this mock postfix prefix and this scope. And next, we define our own custom server, which we configure with our serde-config class that takes in the schema registry URL. This is also one of class we have defined earlier that basically takes in a specific out of the serde and configures it.
So what we want to do is ensure that our Avro schema measurement is handled correctly, serialized and deserialized.
Yeah, exactly. So we got that. Next, we defined the input topic, which is of type test input topic, which has a string type as its key and a power grid measurement as its value. But we do not want to initialize it just yet, because then the data on the topics could carry on between tests. We don't want that, so we will take a late init here to initialize it later, and do the same thing for the output topic. So it's also a string of the type power grid measurement. And we do the same for the topology and the test driver. So this is our initial configuration, and now we will set what we do before each test. So for each test, we want to define our topology, which we use the stateless topology that Herman went through earlier and configure it with our serde. And we also need some test driver properties, which takes in basically a Java properties object, which is basically just a hash map, and we use Kotlin's apply function to configure it before it's saved into the variable. It's a bit tedious to type it in, so I'm gonna cheat for that one. And yes, so what we basically have, we have the necessary ingredients for our Kafka applications with the application config and its bootstrap server. These don't matter too much for this test, but they are needed. We have our key serde, which is just a normal string serde, and we have our value, which is our own custom serde measurement type. And you also need to configure the schema registry used for the test with our own URL. And with this, we can now initialize our test driver with type TopologyTestDriver that takes in our topology, and our test driver properties. And this is necessary because we need this driver that takes because our input topic, we use the test driver to create it with the topic name input topic, and it's the key is serialized with the serde.string type, and the value is defined with the our own serde measurement serde's serializer. And we do basically the same for our output topic.
So what we effectively have here is like an input to our topology where we can type in vectors or whatever data we want. And we also get like an output where we can fetch the results. So just to allow us to test the topology in whatever way we see it.
Yes. So it's quite similar. We just need now to use the deserializer instead of the serializer. And that's it. And now we are almost ready. We're done with the setup. There's just one little thing we need to do before starting the unit tests, and that's to ensure that all the tests are separate from each other. So after each test, we want to reset the test driver, and we also want to reset the schema registry just to ensure that so it drops the scope of our schema registry scope. And with that we are ready to write the actual test. So you remember a case, we have some bad measurement which we make with our record factory, and we set the valid flag to false. We also have some good measurement, which we make in the same way, and it's valid by default. So what we do now is that we pipe these values to our input topic. So we have a bad measurement and a good measurement, and we will read out the output from the output topic. So if everything works well, we should see that the output contains exactly the good measurement. So hopefully this should work. All right, so here we can see we have our bad measurement, we have a good measurement. The output is 1, so that looks very good. And if we continue, yes, okay. Perfect, that did not work last time. So the only thing before I give the word to Herman is that I'd just like to add that you can also use what's called a test record class, and that allows you to pipe in the record keys and the record timestamps. So yeah, Herman will tell you more about that.
Yeah, because in this example we used the Kafka Streams DSL, which is like a method provided by Kafka to simplify manipulation of data. But sometimes the DSL is not giving you the functionality that you need, so we need to make some custom logic, and that is often done with what is called a processor, or PAPI is what I call it, processor API. So what I want to show you was that you can also go into your processor. So this is my stateless processor, which is the exact same thing as the filter. So it's just a log message, and then we just keep the valid records before they are forwarded down the stream. So what you can do with the TopologyTestDriver is that you can put in debug breakpoints. And it's this one, right?
Stateless.
Yeah. So this is the exact same setup as Axel showed. So it's a little verbose when you first make your first test, but then it's just copy and paste between the files afterwards. So it's kind of nice after you made it the first time. So this is the exact same thing. We make a bad measurement and a good measurement, and then we pipe it in, and then we can run the debugger. And then we can like verify our logic by stepping through it if you want to. You could do the same with the DSL, but then you suddenly find yourself deep into internal Kafka Streams logic, and that's kind of tedious to work with. So the processor API is a really nice feature. Yeah. So the last thing, it's often difficult to test things with that is based on time logic. Like every 10 seconds we need to do something. If a record is delayed, you want to throw it away. The TopologyTestDriver makes it really easy to manipulate the time and control the wall clock in Kafka. So here I have a little more complex processor, which is called a stateful processor, which has like a store, which can store data or state. And we also have something in the processor API called a schedule, which runs at a desired frequency. So I think I set this to run every 10 seconds. So every 10 seconds, I think the log message is done. Oops, it's kind of funky.
Sorry.
So every 10 seconds, we do a log. Just log the newest, baddest measurement. And we fetch that from the state. So what we can do in the test is that this test is a little more complex than what Axel showed you, because we are introducing a state or a store, and we're also testing the processor. So when you're testing processors with the TopologyTestDriver, you need to make a topology with that processor. So what we do here first is that we make an empty topology, Then we add a source, which is like the input topic, somewhere we can pipe the data in. And then we add the processor itself. And then lastly, we add a sink. So that's like we have the start, we have the processor, and then we add like the bottom. And we also connect it with the store that we made using this add state store method. So it's kind of trivial to like test processor. So what we can also do with the TopologyTestDriver, as mentioned, that you can control the wall clock. So here you can just specify, okay, which time do I want the TopologyTestDriver to start? So I said like 1 millisecond after 1970, first and first, yada yada. So then we can go to this test where we see, okay, I have a bad measurement that was sampled at time 0. And then I'll pipe it in. And then you have this really cool function here, which is called advanced wall clock, where you say, okay, I got my input, now I just want to progress the time 10 seconds and see what my topology does. So as expected, you get the log message that was supposed to come every 10 seconds. So as you might recall from the schedule, it just logs the newest bad measurement, which is yada yada, which was sampled at 0. And you can also see that the current time is 10 or 1 millisecond past 10 seconds. So in this way, you can kind of test everything. You can pipe in a loads of data, progress the time, see what happens, and then verify that your logic works. So yeah, I think that was it.
Well, we can just, I guess, move from this or not. Yes, that's so bothersome. Now we have to do like this all over again. Hoping to avoid that. But yeah, we have this nice little recap that we wanted to go through.
So people just try to wrap up what the TopologyTestDriver gives you. The benefits is that it's fast to run. It doesn't have to start up a whole Kafka cluster, which can be kind of resource heavy. And it's also deterministic. It removes like all the network calls and all that asynchronous stuff. So it's really good for making unit tests that are part of your pipeline. So like every time you build your image, you can just run these tests beforehand and see that verify that the logic works. Yeah, able to do asynchronous Kafka logic, and it's also really nice that you can use the debugger to just loop through all the steps and like see what's actually happening inside your topology. There are of course some drawbacks. The first one is that it's a simplified Kafka simulation, so you don't have any caching and you don't have any network calls, so you can't verify that that stuff works. So there's often you can have like the logic seem to be working properly, and then it comes up to spin up, and the application kind of behaves funky because of some weird caching stuff. So yeah, you should be aware of that. And yeah, the test can also only run with one partition. So if you have like a load of repartition steps and stuff and want to see if that works, then TopologyTestDriver won't help you. So something to be aware of. But there are some other resources you can use to test like the network protocols and running with more partitions. I think the test container is really nice because there you can spin up a Kafka cluster, and then you can just type in some data and you can just verify that everything works as intended. And yeah, there's some other stuff here as well if you like to read more about it. Mock process context is nice, and if you like to test producers and consumers, you get the mocks for that as well. And yeah, I think the content page for testing clients is kind of descriptive and really nice. Check out.
Right, that's what we had. So do you want to grill us with some questions, or how's it? Yeah, you?
When you perform testing with Kafka applications, do you like combine TopologyTestDriver with some sort of more end-to-end Kafka tests, like test containers, or like how does it work?
We do keep that separate.
Yeah, as I told you, we run like the TopologyTestDriver as a part of our unit tests. And before we deploy out in a review environment or test environment, we do what we call an integration test. Statnett has developed a framework called TopologyTestDriver, which is like in OpenShift, you spin up a local Kafka cluster, and then you spin up a microservices that pipes in data to the cluster, and then you can also connect your application to the cluster just to verify that it can read and push or produce data to a Kafka cluster. So we kind of do an integration test, which is developed here on Statnett, but test containers is also a viable choice.
Mm. Oh, okay.
Yeah.
Do you need a mic or can you?
Can it do a parallelism in testing?
Parallelization?
Yeah.
I don't think so. We haven't tried it, but it's very simplified. It's just like to check that every step of your topology works. So I don't think it can do parallelization, but I think just pipes one record and then sends it through the topology, and then you can pipe it another record.
Mm.
So record by record.
Yeah. Thank you. Because I'm just wondering what if I have, let's say 1,000 tests, and I have this expensive CI tool.
Yeah.
Right.
Yeah. Okay. Yeah. Run the test in parallel, or yeah, you can probably do that because I think it's you can as we did, we make our own topology at every test, so it doesn't interfere with each other. So yeah.
And it's not flaky.
No, it's not flaky. It's supposed to be deterministic. That's like one of the key points.
Mm, mm.
That's good. Thanks.
Have you used it to test any non-Java Kafka Stream stuff?
It's got lid, so det står count.
JVM. No, we are mainly just using Kotlin, so that's what we've been having experience with.
Mm. Oh.
Question. Another one. Just in your development principle or whatever, do you also test those dead letter queues?
The letter queues?
Yeah.
Not really. We haven't explored that yet because often we get like our data from the source system, SCADA system, and then we do like all our data cleaning there, and then we are responsible for the data down the streams. So yeah, we should probably have some dead letter queuing, but as of now we're just trying to
Happy path.
do the happy path, and if something is going wrong down the line, it's our own fault, so we should blame ourselves.
Yeah, well.
What do we mean dead queuing? What?
Yeah, if there's some bad data or something that you can
Or up that data.
just process in another task. Kind of, you get all the good data going there, and then some weird data, and you can process it in another task. Kind of.
But now they're like basically just dropped if you have some.
Yeah, we do. We make our decision at the start of the value chain because that's where we get like the raw data, and then we are responsible for the rest of the value chain. So yeah, we are trying to make it easy for ourselves by doing all the cleaning at one point.
And we're developing some fallback solutions, like if at least if the data stream goes down from one source, we can switch to another one.
Yeah.
So there's something.
So to build upon your question, so it's possible to test other non-Java Kotlin Kafka.
Yeah, I think it has a wrapper for other languages, I'm sure. That's the rest of the Kafka library. It's a part of the Kafka library, so hopefully the people maintaining the wrappers have included the test wrapper.
Yeah. Any other question?
If you would like to integrate with the cloud.
With the cloud?
Yeah.
This is for, I think, local testing.
I know, but if you had an option for that,
I'm not.
will you go for AWS or Azure or?
Well, for deploying the, or like not developing the microservices yourself, or what? Are you?
Instead of on-premise.
Oh yeah. I think Dino is a better resource to ask that question. A disclaimer: I'm just making the applications which runs on the platform, but Dino is the one managing the platform itself. So
The question is, it depends.
it depends. Yeah.
You know, it's.
But it's mainly about money, right?
Everything is about money. Exactly.
Any other question?
It's not directly about testing, but have you ever encountered memory issues with Kafka?
Oh yeah, several times.
Several times. Especially many of our applications are stateful. They have a lot of state stores. And by default, these state stores are limited with how much memory they can use. So yeah, when there's a lot of back pressure, a lot of data coming in, sometimes these stores fill up and crashes our application. Monitoring is first key to like try to create alarms to check like if the memory usage is going really high, and also having a good store logic for storing data. Maybe you don't need all the data when there's a lot of back pressure. Many of the measurements are old. Maybe you can just discard them. You have to take that into consideration, I think. And I don't know, memory is cheap, so you just give it more.
Great presentation, and it seems really useful, but also there's a lot of boilerplate. So do you guys have this as sort of a template project that's just automatically injected in a new project, or is it like copy-paste?
Yeah, it's pretty much copy-paste. So the template project, we do have like a template project which we use as a baseline for other projects with a lot of tools like change this, change this, change this. So, but we actually prefer it that way. We have had the instance where okay, let's just gather it into one base project and every other inherits from that project. But when something goes wrong, then you have to go back to like the base project, and it was a bit of a hassle. So we actually concluded that it's better to just copy-paste it every time to make it simpler.
But yeah, you can probably make some annotations that automatically does everything for you.
Probably not related to your demo. Just wondering if the consumer services that are deployed are in microservices.
Yeah, they're in microservices. So we're trying to make our applications as small as possible and the topology as simple as possible, and rather divide the logic across several microservices. So,
and then how do you do the horizontal scaling out? Do you does it get triggered with using an event, or through a CPU usage, or what else do you use for
spin up more
triggering the event or scaling it out?
Yeah, spin up more like applications in our OpenShift cluster. So because Kafka have this consumer groups, so you can just run a bunch of them in parallel and consume a bunch of data like simultaneously.
First step is to like try to assess how many partitions you need in your topic, because that's what limits the parallelization. So if you find a good value for that, then you can spin up more pods to compute or process the data in parallel, or just give it more CPU, I guess.
What about message order? Is that important?
Oh, yeah, sometimes. So then you need a partitioning strategy, because the messages, you expect them to be in order for each partition. So yeah, you need to ensure that what you need are partitioned rightly, and what's you can deal with later, you can have cross partitions.
So Kafka guarantees ordering within a partition. So the MRID field that I showed you in the schema, which is like identifier for a sensor, is a really nice key. Because then you get like, for that sensor, you get it chronologically through the value chain. So,
but if you run multiple instances of your consumers, right?
Yeah. So then they can like each take a subset of the like generators, for instance. So you have some logic that is dependent on that we get the power measurements in chronological order for each generator. And we have, if you have thousands of them, then you can split the generators across partitions. So that's, yeah.
So choosing a good key is important.
Cool.
Yeah.
Thanks, guys.
Thank you.
I forgot to say the toilets are just out, left, and then right. Priorities there as well. I think we'll have a 5-minute break, and then we'll talk from Kim. He's actually disappeared. So yeah, we'll be back in about 5 minutes.